Now, there are several other very important things to keep in mind with all of this. Let me also just kind of separate these just so you can see. These are all separated. There's one piece up above that's proportions, and there's a piece down below that's means. Now, what are some other things that we've run into in this chapter that are very important to know? Well, first of all, the alpha and your confidence level are complements of each other. Right? Complements we learned in chapter 5. It means they add up to 1 or 100%, same thing. Next, the interpretation. So the way this always works is we are whatever confident that the true population parameter is between the lower and the upper confidence interval limits. So you'll say between the lower and the upper. Now the thing is that the hard part about this is that true population parameter business, because that could mean proportion or it could be mean, and it has to have context, and that's the hard part. You have to figure out what the problem was talking about. Usually it's in the problem somewhere, but you have to include it. It has to have the context with it to be valid. And these upper and lower confidence level interval limits may include units. So give units as well for the upper and the lower. Oh, I already wrote this up above, but I'll say it again. I thought I had it somewhere. It's the point estimate plus or minus the margin of error. Right? That is always the basic formula for what we're using. Now, the point estimates, we've talked about them up above. The point estimates, the real things, are p hat or x bar. Now, the thing is that sometimes we can find them a different way. So we're going to have kind of a backdoor formula, kind of a cheating formula to be able to find them. So the point estimate is also the lower plus the upper divided by 2. And the margin of error is the upper minus the lower divided by 2. Now these are formulas that only work if we know the interval. So we can only use I'm going to call them the cheating formulas because they're not the real ones. The real ones are up above. Like that's the real formula for margin of error. But you can only use these kind of cheating, secondary. I should use the word secondary. So these are not the primary. They're not the real ones. They're the secondary ones. There, that's a little better. So we can only use these secondary formulas if the lower and upper are known. I shouldn't say given, known, because you can find them, right? So are known. Most often they'll be given to you in the problem. But you have to have them. You have to have your lower and upper in order to be able to use those formulas. Okay, next. What about the relationship between those? Oh, one other thing before I walk away from this point estimate. Just a reminder, the way the picture works, because it's always good to keep in your head what's happening. Your point estimate is here in the middle. You get your lower over here. You get your upper over here. The confidence interval is this in between. The error is right here and right here. Right? Okay, so now for the last bits. The relationships between sample size and margin of error. Well, we learned that in section 9.4, but suffice to say that sample size, which is n, and error, and wherever error goes, width goes, because the width of the interval is this whole thing here. The width is that. The width is twice the error, right? So in other words, error and width are basically the same thing. All right, so if your sample, let me put it this way, they have an inverse relationship, which means that if your sample size goes up, then your error goes down. So I just want to segment this off because I don't want this to confuse us. So these have an inverse relationship. So if sample size goes up, error goes down, right? So if n goes up, error goes down. Or vice versa. If n goes down, then error goes up. Sorry, I ran out of space there. They have an inverse relationship. These have direct relationships. So they're more straightforward. So if confidence level, C level, goes up, error goes up, right? Or if confidence level goes down, error goes down, right? So C level goes down, error goes down. If C level goes up, error goes up. They have a direct relationship. And then down here, this is standard deviation. This is S. If S goes down, error goes down. If S goes up, error goes up. Now there is one other extra piece to this that I want to kind of throw in before we're done with this sheet, which is that I don't usually ask the questions this way. So I usually talk about narrowness. You know, what makes the interval narrow? So let's just a reminder, let's make a note here. I'm just picking a color here. All right, so the note right here. When I ask you, or your professor, your instructor asks you, what makes the interval narrower or narrow? Narrow means it's shrinking, means the width is smaller. And if your width is smaller, that means that your error is smaller. So the interval is narrow means that the error or the width, same thing, right? I'll just write that, width are smaller, right? Means the error is down. If the interval is wider, that means that your error, right, if it's wider, it's stretching. So the error or the width, same thing, basically, are larger, which means your error is going up. Right? So if I say to you, you know, what makes the interval wider? The interval wider is here, right? Interval wider happens when your sample size goes down or when your confidence level goes up or your S goes up, right? So the interval, error, let me put it this way, error goes down if your N goes up, your C level goes down, and your S goes down, right? Those are the three that go together. And your error goes up, right? Up, up, up. If your N goes down, see, that's an inverse relationship. That's the opposite. C level goes up, S goes up. Those all tie together. Sorry, my word C level there got weird.